central limit theorem. We're going to try to prove it. We've got a few preliminaries to get through so that we can understand what we're doing. So the mathematical level in this class will pick up, but we're really picking up with your first calculus class. Essentially, it's all 1 week. I'll try to remind you about some of these devices that we use, and if you're ever just totally stuck, you can ask me to fill in the gaps. If there are facts that you hear and you're not sure about them, review session is always a good time to ask me about details of something. So I like to make this class a little bit engaging, conversational, big ideas, but on, and I said it again, the Wednesday review, I mean the Thursday review. So on the Thursday reviews, then I can break down and do more of the problems on the board. And so I think it would make a really bad 9 a.m. if I just integrated it. And so I still do remember how to do it. And so if you want me to work through some of these things, Thursday reviews is the best time. Of course, we'll try to interject some of the stuff to keep the conversation fluid. This lecture tends to be a little bit more mathematical than all of them. So we'll kind of flop back and forth, try to go big ideas and hone in on details. But what the central limit theorem says, and this is almost correct, whatever this distribution is, we don't know it. So let's say we don't know what this distribution is, and I'm not even willing to try to figure it out. But if I collect samples from this arbitrary distribution, and they're IID samples, so, and we can probably drop some of that. The theorem's a little bit stronger, but in the version that we're going to look at and prove, we're going to be dealing with IID-ness. I'll talk a little bit more about this when you have dependence and things after we get through the proof. Obviously, depends on what the dependence is and how fast it moves, how variable the dependence is, to see if there's some sort of normality limiting theorem. But if all these samples are IID, and I form X bar, then this X bar is very close to a normal distribution. That's at least how we practically use the central limit theorem. Central limit theorem says something a little bit more precise. But regardless of this distribution, and I don't know what it is, I can say what the distribution of X bar is, the arithmetic mean. So it has a very important property. It tends to be normally distributed. Now I say tends and approximately because that's how we use it, but I'll show you the precise limiting theorem in a moment. I haven't said this correctly. I said for any f I can do this, and it's normally distributed. And we know that's not true from last lecture. Some of you named a distribution where the central limit theorem doesn't hold, Cauchy. And so we need some properties for this distribution. All distributions integrate to 1, so we don't have to worry about that. But I need a property for this to be true. Does anybody know what the minimal property is that I need for the central limit theorem, i.e. X bar to be normally distributed?
Variance should exist.
Variance should exist. Variance is finite. So this is if variance for my samples exists. And I'll just write it down like that. Less than infinity. It's an actual number. So Cauchy distributions don't have variances. If you try to compute it, you compute infinity. They don't have means either, which make them real fun. They certainly have central tendencies, but it's not well described by the arithmetic mean. We'll talk about that after we get through the proof a little bit. They have a dialogue in the book on that, but we need this variance is finite. And that's the minimal property that we need. We will not prove it with just this minimal property. That proof is rather long. And so that's in Deller's like 1968 book, if you'd like to look it up. And so, and we'd probably have to increase our mathematical level a little bit to get through that proof. So there's a lot of variations of these proofs about X bar. Like some people say, oh, it goes towards the mean. Central limit theorem says a little bit more. It says how it varies around the mean. But the law of large numbers says that this number tends towards the mean. And then we have these versions of the law of large numbers. Strong law, weak law. Are they different? A little bit. So what's weak law and strong law? It's all about how it converges.
One relies on convergence and probability, the other is pure convergence and limit.
That's right. Well, yeah, exactly. So an almost sure condition that it gets close to mu and it stays there. or can it periodically pop away from you? It turns out X bar converges in the strongest sense, so I might say, why do we use the weak law of large numbers? Well, if you know what the moments are, maybe you can say something about its tendency, but you can't say that it converges in such a nice way. But also, realistically, the reason we do these things is so we can prove them quickly in the classroom. So proving it in the strongest sense requires more chalk and more mathematics. But I can prove something kind of like it that's a little bit weaker. And so I'll prove something like the central limit theorem, but I'll broaden my assumption set. So we'll prove it the way the book proves it, and we'll assume a full set of moments. Saying that, the central limit theorem doesn't require a full set of moments. It requires the first two. So if this one exists, then the first one will exist as well. They cascade like that. And so this doesn't guarantee the higher moments exist, but it will say the lower moments exist. Okay. Let's get through a few preliminaries, but before we do that, I got a good question after class last time. So Elise came up to me and said, why'd we have to do that bootstrapping thing? Because you basically showed this bootstrap thing was normally distributed, you computed a mean, and why can't I just estimate the variability in this thing we're computing, the mean, using plus or minus 2 SDs, 1.96? Good question. If you were just computing the mean, you would invoke the central limit theorem, and you wouldn't do bootstrap. Probably invoke it and make sure that you have enough samples to approximate everything with a normal distribution. So that's a good example just to show you that bootstrap kind of works, and it does about what it's supposed to. That's what we saw. But let's look at a different example where the central limit theorem doesn't apply. And you might know what the theoretical distribution of this statistic is. I'll get this uploaded on the website after class. But let's just go back to this bootstrap code. Same exact stuff. The only thing I'm going to change is the statistic of interest. So instead of looking at the mean, I'm going to compute the variance. That's a statistic of interest. Now the variance, you might say, why would you want to compute the variance for a trimodal distribution? Does it mean anything to you? And for me, it really doesn't. It would be a poor description of variability in the model because there's groups, and I want to know how they vary within those groups. We'll talk about that later. So, but if I were just talking about averages of the entire thing, the average sits in the middle and it doesn't really reflect the trimodal nature of the distribution we've created. If I were just interested in means, then variances would be a good way to characterize the uncertainty in the mean. We'll get around to that later. But let's just change the statistic. So central limit theorem doesn't apply to this, does it? It's not X bar. This is sum of the xi's minus X bar squared divided by n minus 1 is the way this code does it, square root over the top. That's their variance that they're going to compute. And I'm going to change it down to the bootstrap as well. So the bootstrap will do the same thing. We can see how well the bootstrap does, but then we can also ask the question, does the central limit theorem apply to this statistic? And it doesn't. But we'll check it using a QQ plot in a moment. I want you to just quickly get a handle for QQ plots. Let me just show you an aside a couple QQ plots because I think some of you aren't used to looking at them. I have another really good question at the end of class. What does it mean when it's flipping around away from the line? The straight line in a QQ plot. So let's work with a distribution maybe we know something about. This is a T3 distribution I'm going to sample from. So I'm going to grab all these and I'm going to plot the quantiles from these 1,000 replicates from a T3 distribution against the quantiles from a normal distribution. We'll see how they compare. A lot of you have done this and seen this before. You know what it means. So there's my samples. I'll just make a quick QQ plot comparing against the normal, and this is what the QQ plot looks like. So T distributions kind of look like normals in the middle, but their tails are different. And so this side of everything being lower than the line, is saying that I'm heavier tailed on the left side. And everything going bigger than the line on this says it's heavier tailed on the right side.
Lighter.
What's that?
Lighter tail? On the right side.
No, she has heavier tails. The T3 has heavier tails. Everywhere. They're heavier everywhere. So the normal tails, I don't care where you centered it or what the scale is, the T3 tails are gonna put more mass and the normal tails are gonna duck them. So heavy tails means it's thicker. So anyway, I'll let you think about that. A little bit of a mind bender, but hopefully you know what T's look like compared to normals. So this is a common diagnostic plot. It's one of my 2 favorite plots. What's my other favorite plot? What's your other favorite plot? Do you have favorites? And I'm not going to tell you what my other favorite plot is. You won't tell me yours. And get rid of that mohawk. Keep thinking about it and draw pictures and make QQ plots. So when I see the tails flip in those directions, I know I'm comparing it to something that has heavier tails. If they had lighter tails, they would bend the other way. So let's just go to my bootstrap code. I'm going to compute variance, see what it does, see if the bootstrap even works here. We'll run that thing. So I'm computing variance for each one of these samples and going back out into the population. These are my repeated samples. And then I'll bootstrap the last data set that I have, just the last one. We'll see how that works, and I'll bootstrap it a bunch of times. We'll see if the bootstrap's working, and then we'll see if the central limit theorem applied. Okay, so bootstrap kind of works. So I plotted a QQ plot with 2 sets of empirical samples, one from the replicated population and one from the bootstrap distribution. Looks pretty good. I like that. I'm good with that. My eye says fine. So this is my experience over 20 years. Yeah, it looks about right. That's about as good as you get. We'll point out that if you did do a chi-squared test to see if the distributions matched, something like that, or a G-test, or whatever your favorite test is, if you had huge sample sizes, it would look at this and say, nope, not the same. They're not the same. They're slightly different. And so eventually you'll get a low p-value saying it's not the same, but it's because the n is so big in all of this. We have to discuss that later in this class. That'll be a big topic in this class. So I don't like testing per se. I trust my eye better. Okay. Now let's check the QQ plot. These are the 2 histograms. I can never eyeball a histogram and tell you if they're the same. I plot a QQ plot. Let's look at a QQ plot of, we can look at either one, the replicated stat or the boot stat. I'll look at the replicated stat because this is the right thing. There's no bootstrap approximation in it. So rep stat, and it looks like that is the QQ plot. Is that straight? Is it following the line? A well-trained QQ plot is, would say no way. And any Stat 101 student would say, no, that looks pretty bad. This is horrible, matching. It doesn't match well at all. And so I have some heavier tails over here, and then I have some lighter tail on the other side. Does anybody know what that distribution looks like? It looks way skewed to the right. The bulk of the mass is on the left. Skewed left and right always confuses me. I'm going to flip the one. So it looks like this. The distribution of this stat, well, we just saw it, but it looks like it's, I'll just say, hist again, figure. Let's make another figure. Hist rep stat. Big skewed thing. And so, super skewed. Anybody know what that distribution is?
Is it a beta?
It's not a beta. We could do a sanity check, and I'm going to ask you this over and over in class. Like, did you do the first sanity check? Where do betas live?
0, 1.
0, 1. Not a beta.
Is it a gamma?
Maybe. Definitely relates to a gamma.
Is it chi-squared?
It relates because gammas and chi-squareds are very related. It's scaled weird and it's kind of flipped around weird. So, but that's kind of cool. Nice thing about the bootstrap is I don't need to know. I can still use this. So if I did this histogram with the boot reps, the boot stats, I don't need to know the answer to the question. What is this distribution? I don't know. That's what the bootstrap gave me. So I can quantify my distributional uncertainty. I think the best quantification is the full-blown histogram. But if you wanted to create intervals or centers or anything like that, you can do that. I kind of like the whole histogram as the whole representation. In 1D, I'll always just take the distribution to show it to me. So anyway, so central limit theorem doesn't apply here. Bootstrap does something for us. And from our diagnostic of comparing to the rep stat, we know that it's doing a good job. So even though we don't know mathematically what distribution that thing was, we can use it. And we're not using any limit theorems. So central limit theorem applies to sums, arithmetic sums. That answers your question, right, Louise? So, yeah, certainly, if you have X bar, you want to talk about it, probably don't use the bootstrap. You'd look a little silly doing it. I use it as a demo in class. But for statistics I don't know anything about, and this is the thing we want to compute, what we're trying to measure, and I want its distribution. The bootstrap's a really cool tool if your samples are IID. But be careful, bootstrap won't always work for you. So we need other tools. So when will the bootstrap fail?
Do you have a small n?
Small n will do it. So how small does n need to be? You know, it depends on how wiggly that distribution is. It's surprising that even when we use like 10 or 15 points in that tri-mode distribution, it did okay for computing things like the mean or the variance. But small n is the thing that kind of kills you on it, but also the nature of the problem. Let's think about this. What if I wanted to compute the median of a distribution? And I wanted to know how uncertain the median was. So I could bootstrap over that and it would give me some distribution over the median. So bootstrap replicated samples, compute the median, plot it. What about the max? See, you're trying to estimate like the max of a distribution, like in that uniform problem we were looking at. I'm trying to compute theta. And I've got a sample, and I bootstrap over it and I compute the max. What's going to happen to that max? It's always going to get pulled to the left a little bit. I'm never going to see anything to the right of it. And so the bootstrap can't give me that. So the bootstrap would be a poor tool for estimating uncertainty in the max because it's going to always be biased to the left. So got to think about the problem at hand, check. But if you did do a simulation and tried to see how well the bootstrap worked on estimating theta in that uniform example that we saw, it wouldn't do very well. So we probably need to do some math. Okay, so different statistical devices depending on the nature of the problem. Sometimes it's an asymptotic issue, and sometimes the nature of the problem is just harder. So the bootstrap doesn't work well in trying to estimate things close to boundaries for fairly obvious conceptual reasons. Okay, so central limit theorem. We need a few devices to follow the proof in the book. And that's Taylor's theorem. We need to know about moment generating functions and this creature right here. Let's start here. Everybody's seen this, right? Everybody knows it. This is high school. I saw this for the first time like when I was a sophomore in high school, and I went to a bad high school. So, is this not clear? I like to do this all through my career. I know this is true. Definitely true. How would I convince somebody if they didn't know it was true if I were in high school? Well, I would plot this thing for big N, and I would see what this function does. So e to the x is this increasing function. So it's getting bigger and bigger and bigger. So it's this increase sort of thing. And so that's what it looks like. So if I plotted n, if I made n real big, then I would get numbers around the line, and I could convince somebody that that were true. Do you guys know how to prove this? I like to ask myself that all the time with these basic calculus things. Could I teach that? Could I prove it? David, you're the only one in the class, right? You're not even.
I don't even know if I could be honest.
Ben?
So, you compute the limit of the log?
Yeah, it's true. So the proof does look like this, and Ben's reviewed his calculus book a whole bunch of times. Go to your calc book and see what the proof looks like. But you end up working with the definition of the derivative of the log. You take that limit. We know what the derivative of the log is in the proof. It's 1 over x. We're working with a natural log. And comparing that to the limiting definition and knowing that log 1 is 0, things like that, you can prove this statement. So if you're rusty and you want to get better at things, every time you see something that you're supposed to know or like to explain to somebody, look it up in your calc book. If you want me to prove this, I do that in a review session for you. So, but I like to ask myself the question, am I capable of doing it? And for me, if it's like, yeah, I kind of remember what it looks like. If I don't, I go to my calc book or Wikipedia. Okay, we're going to assume you know that right here. If I change this right here, some function of x, that would be a function right there. If I turn that into a negative sign, that'd be a negative sign right there. E is a fascinating number. So it's the only, this function right here is the only function such that the derivative is equal to the functional height, and all of the derivatives are equal to its functional height. So all its rates of change are the same. It's kind of amazing. So that number pops up all over the place. We'll point out that in the central limit theorem, that number pops out again, that this distribution has a whole bunch of really neat things that pop up. We see E again, 1/2 x bar, and I should write root n over here minus mu squared sigma over root n. So that's a normal distribution. Okay. Moment generating functions. Let's just go back to this. We're going to use that fact right here. That limit, that will appear. Moment generating functions or Laplace transforms, they're used for the same reason everywhere. So if I were in physics class and I were trying to use this thing, I would still be taking derivatives with respect to t. That's just expectation. This is a linear operator. I can slide that right through it. And so this is just going to be x e to the xt right here. When we evaluate this at 0, so plug in 0 right here, this becomes a 1. So that's expectation of x. And if I take the kth derivatives and I set them equal to 0, this is going to provide me the kth moment, the distribution. So the second moment with the first moment I can use to get the variance. So in physics class, when I learned about this, you might have some distribution right here, the way they explained it. In the example I saw, was you can imagine this is a bar right here, a metal rod. And its mass of the bar is modeled by that curve. And so the question is where would I stick my finger to balance this bar? That's the mean for us. It's characterized by the first moment, but this is the center right here. So that's where I'd stick my finger, right there. If I wanted to compute the second moment, I could get this quantity sigma out of it after untangling it from mu. And in my physics class, they characterized that as if I had this thing balancing and if I wanted to spin it around, what is its tendency to spin, the inertial moment? In statistics, we're talking about variances. So a lot of these things are the same, and we'll see them all over the place. Does anybody know for a normal distribution? So x is normally distributed with mean mu, variance sigma squared. What is the moment generating function? E to the xt. And this is just an integral, e to the xt. And then I plug in my sampling density. So I'm integrating with respect to the random variable. This is 1 over root 2 pi sigma e to the minus 1/2 x minus mu squared over sigma squared. Make that e better, bigger. And so I just want to integrate over this thing. Integrate out x. There'll be no x's, but there'll be a t left over. So anybody know how to do this integral? If you've taken the prerequisite class to this, the probability class, or if you've read through the first couple chapters of the book we're using, they would have you compute this at some point. And so, real quickly, how would you compute this? Remember where I'm integrating over the whole number line. That's where x lives. How do you do it? If you convince yourself you know how to do that integral, could you solve a basic probability class? Basic probability problem. What's the technique?
You like push the xt into the into the other e and pull out whatever constants you can, and then expand the x minus mu squared and
Expand it.
x minus mu squared times x is squared to take the x squared minus 2 mu x.
Okay, you got it.
Yeah, and then you can take out all the mu's and anything that doesn't have a t in it, and then you get to recognize the kernel,
Okay, and?
and it ends up being, I don't know.
Yeah, and you're about to make a mistake. You need to complete the square along the way so that you can get the integrand to integrate to 1. So what you would do is you would factorize all the stuff out that doesn't depend on x in all of this. So there'd be a mu squared term, you could take it out. And then I'd complete the square and I would be able to integrate the distribution. Eric?
So I have a question on the density of the CLT. Is that,
Yeah, squared right there. Yeah. Yes, thank you. Definitely when I make little typos or if I announce things incorrectly, call me out real quick. So Eric's 2 for 2.
You have to put a square root over the end as well.
Yes. Thank you. Absolutely. That's embarrassing. So, but yeah, the whole thing needs to be squared down there. Okay, so this is a completion of the square exercise. You do this about 3 or 4 times a year. You know, this exercise, I do it all the time. If you've taken my base class, you've done it a lot. So, if you guys want me to compute this for you, I could, and I would be happy to do it at review if you're stuck on this. But really, these are practice problems for you. This is just review from your probability class. Does anybody know what the answer is off the top of their head? So, here's what I would do if I were trying to do this proof or something like that. A lot of times I don't like getting bogged down by the integral, but I only do that if I convince myself I know how to do it, and I could do it. Then I'll just shortcut it and look in the back of the book. What's the moment generating function for a normal? And I could look at wiki, and I could get it real quickly. So what is it? Somebody knows.
T mu.
What's that?
T mu, I believe.
T mu? No. There's an E in here.
Oh, T mu. T squared.
You guys are good. That's it. That is it. So this is just an integration problem. Okay, we'll come back around to this. We're going to use that later on. Taylor's theorem. Same question. Now, obviously, I really like this because I need to assume certain things for this to be true, this equality. What do I need to assume is true for this to be true? What did they teach us in calculus?
The derivatives have to exist.
Yeah, the derivatives exist. And they're in the equation. So if they didn't, you can't compute it. And so it's kind of neat. So sometimes you'll find that things are too wiggly. So when things get real wiggly, we don't use Taylor expansions. So basically, this is a criterion on how smooth everything is. Taylor doesn't just say this. He says how good a finite truncation of this thing is. And so if we ended up looking at just this, I'll say I goes from 0 to 4. I'm going to write in the fifth one, just to be clear about this. What Taylor said was, let's say I wanted to use this as my approximation. So I only want to use the first 5 things in this polynomial to approximate.
Is the I equal to 1 or 0? Or am I missing something? There's an I equal to 1 on the left and an I equal to 0 on the right.
This goes from I1 to infinity.
And then that one goes from 0 to 4.
0. Oh, sorry, you got it. This is 0. Yes. So all the cobwebs come from. Yeah, that's 0. Thank you. This is my approximation right here, and here's my remainder. What we learned in calculus class is to compare this term to that term. The biggest term in your approximation to the smallest term in your remainder. So it's this term right here that governs how good the approximation is. And we learn things like, if I compare the ratio of this to that, and I see where that thing doesn't explode, then it will converge well in that radius. And so we can define radiuses of convergence. How far can X go from C before this term right here explodes compared to that one? So that's what we're always comparing. So that's Calc 101, your Taylor series sort of thing. So we're going to be comparing the ratio of these 2 terms right here when we do a Taylor expansion to show that this is small compared to that, at least asymptotically. Okay, so that's what Taylor's theorem is really about. It's governing the air with this term and comparing these 2 terms to see where everything converges. So again, a mini refresher from your calculus class. If we don't remember these coefficients right here, it's just a polynomial expansion and we've got these coefficients. Could you all derive what the correct coefficients were? Could you prove it? So again, David's like, heck yeah, I can do this one. Easy piece of cake. This one is kind of easy. I thought this one was cool because I could remember it all the time. Chin, what do you think? You could too. Kid stuff. So let's just remind ourselves and then we'll get on with the proof. So let's just say I didn't know what the coefficients were. So when I put it as 0 right here, this is just 1. So the first term is a constant. So let's just write down our coefficients. C0 plus C1, x minus c, plus C2, x minus c squared, plus C3, x minus my centering parameter, 3 plus 5. So don't mistake my centering parameter for my coefficient right here. So if I wanted to know this, if I wanted to know C0, I plug in C into the whole thing. So F of C is equal to C0. If I wanted to know C1, what I could do is I could take a derivative of everything. It'll kill that term. It'll turn this thing into a 1, and I'll be left with C1. And these, I'll have these little numbers coming down. So let's just write down F prime is C. So this is just going to be my first derivative. I'll call it F1. It's just going to be C1. If I do it again, F2, C. Second derivative, that's a 0 now. That's a 0. This comes down, so this is going to be 2 times 1 when it comes down. This will be 2 times 1. I'll write it out like that, times C2. And then I can solve for C2. And we can see the pattern that forms. And so, again, it's kind of one of these really neat proofs that you just do it. So, solve for them. And at the end of the day, we get these coefficients. All reminders. Any questions about all our preliminaries? Because we're going to use all 3 of those. We're good? Let me ask one more question. Is that a waste of time? No. One of these days, I'm going to get you guys to like use words. I'm happy to go through your calculus with you during review. If you want to see proofs, I kind of like to see if I can remember them too. Could I teach that class? I'm supposed to be able to. So I think I could, but practice is the key. Okay, CLT. Here's what we're going to check. Here's what I'm going to say first. Here's actually what the central limit theorem says. So it says x bar n minus mu over sigma over root n, right here. N goes to infinity. This thing goes to a normal distribution. With 2 parameters. With mean 0 and variance 1. So that's what this actually says. So the central limit theorem should, no, you're good. Okay. So central limit theorem says this thing is normally distributed. So as I crank up n and I generate these IID numbers from whatever distribution, this thing flutters around this distribution, 0, variance 1. So that's how much uncertainty there is right here. The standard error in the actual X bar estimate is this thing right here. Okay. The practical CLT says something a little bit different. This is what I call a practical CLT. So this is what I've been saying in class. This is actually correct. And this other thing is not quite correct, but it's how we use it. This is just the standard error. Sometimes I write the variance over there, sometimes I write the standard error. You should be able to move between the 2 things. Just wanted to parameters to look the same. So n goes to infinity. What's wrong with this statement?
When n goes to variance equals 0.
This is going to 0 right here. So we always use it with finite n. And so we use it like that. We plug these things in, and possibly we estimate this thing that's converging to true sigma using a typical estimator like the MLE or the unbiased form. But this isn't what it says. So if I take the limit, this is a degenerate distribution. So the correct interpretation is this. Okay, so subtle difference, but at the end of the day, we always plug this stuff in. Mathematical nuance, but I think that one's kind of important. Okay. Our proof of the CLT will show MGF, the moment generating function, for this statistic, x bar n minus mu over sigma over root n, goes to e to the 1/2 t squared. You'll recognize this as the MGF of a normal 0, 1. So if I took mu in that equation that we wrote down to be 0 and sigma to be 1, this would be the MGF. So we're going to show that in the limit, as n goes to infinity, the moment generating function for that limits to this. And we'll be done. Elise?
What's subscript n? You in this sense?
I like to remind you this is a function of n, is all.
Okay.
So sometimes I don't write it down, but anytime I'm taking a limit or something like that and I'm operating on n, I want to see every place it appears. So it's just a reminder to let you know that I had an n in here that I divided by. I summed n things together. So the limit is happening both here and here. So, okay. See how far we can get. We've got 5 minutes. See if we can at least do the first part of this. Then we'll pick up from there and do the technical part. So I want to just convince you real quick. If I ended up writing down, if I write down yi is equal to xi minus mu over sigma. So this is just the standardization of each individual data point. Then sum of the yi's divided by root n is equal to x bar minus mu sigma over root n. These are equivalent to each other. So this is just an algebra problem if you want to convince yourself. So we could do it. Sum of the xi's minus mu over sigma over root n. I goes from 1. So like this. 1 over root n. This is that. This is equal to n times x bar minus n mu over sigma. And I got a 1 over root n right there. So I've got 2 root n's right there. So I can get rid of those. Divide this one. So new name for standardized random variable. Step 1. Just algebra. So we're going to find the moment generating function of this thing, which now we write like that. What have we done? We got rid of the mean and the scale, and it's convenient. If we didn't do that, our proof would just look a lot messier. Okay. This is probably the hardest part of the proof. I'm going to write down my moment generating function. So I'll write down my random variable down here. I want to figure out what this thing is. This is just the sum of the yi's. I've dropped the index divided by root n right here. Just want you to remember what this is. This is the expectation of e to the sum of the yi's over root n times t. It's just all it is by definition. I want you to see something. Take that root n, move it there. Okay? I can slide that thing over there. And I can take this and I can write it like this. y1 dot 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 to e to the yn. Right here. These are all IID, so the expectation factorizes, and this becomes a product of moment generating functions. So if you play around with these, you can rewrite everything like this. I can look at the moment generating function for each y, t over root n, because this will factorize, because these things factorize the e's, this will look like this. E to the yi t over root n raised to the nth power. So that n is just all of these other things. These are IID replicants, so I get to drop my I. They're all the same random variable. So moment generating functions 101. So this moment generating function, by basic identities, is that moment generating function. Okay, we have 1 more minute left. We're going to Taylor expand this. This is where this proof goes. So I'll have a Taylor expansion, and I'm going to write down the first 3 terms of that Taylor expansion. The first 3 terms in the Taylor expansion, and we'll come back around to this, are going to be m0 t over root n y. m1, the first derivative of this thing, t over root n, and the third term in the Taylor expansion, t over root n. All for random variable y. Somebody help me out real quickly. Do we know that? I know this for any distribution. I can tell you what the number is. I also know this one. I also know that one. Now, I know this one and that one because of the substitution I did. I want you to come back next time and know what those are and why. And then our proof proceeds very seamlessly. I'll help you out. This is 1 because distributions integrate to 1. This one is 0 because it has mean 0. This is the first moment. And this one is 1 because the variance is 1 and the mean is 0. So study that for a moment. We'll come back next time and go through all the details. Thanks, you guys.